Hello students, in this video I'll be taking some problems on Fourier series. So in the previous video we derived the expressions for properties of Fourier series. So we took all the 9 properties and we derived the proof for them as well in the previous videos. Now in this video I'll take some basic problems on Fourier series, and here we will deal with different kind of signals and how to plot its magnitude and phase spectrum here. So there is a problem given. Find the Fourier series for the signal x of t is equal to sine omega naught t and draw its magnitude and phase spectrum. So this is the problem given here. So let's find out the solution for this and draw the magnitude and phase spectrum here. Now given x of t is equal to sine omega naught t. Okay. So now let's express this in terms of exponential. So that is sine omega naught t. We are expressing it in exponential means. So sine theta can be expressed as e power j theta minus e power minus j theta divided by 2j. Okay. Now based on this, so we can express sine omega naught t as e power j omega naught t minus e power minus j omega naught t divided by 2j. Okay. So I can split this e power j omega naught t by 2j minus e power minus j omega naught t by 2j. Okay. So this is my x of t now expressed sign in terms of exponential. Now comparing with synthesis equation of Fourier series. Now the synthesis equation we have x of t is equal to summation k equals minus infinity to plus infinity x of k e power j k omega naught t here. Now this x of t given, I will just rewrite this. We can express 1 by 2j e power j k omega naught t minus 1 by 2j e power minus j k omega naught t. Now if you observe these two, okay, this summation we have the same e power j k omega naught t, so both of them. And here one more thing we have to consider, that is these values. What are these values here? Okay, and I think in the given we don't have k, I guess, just omega naught t here. I will just write k j omega naught t and j omega minus j omega naught t s. If you observe this, in place of x of k we have 1 by 2j and 1 by minus 1 by 2j here, but observe this, we have value for k here, and here k doesn't exist, but the value of k has been substituted here. Now that means if the value of k here, if I expand this by applying the value, I can see this. To get these two values, I have to put k is equal to 1 and k is equal to 2. That means I will get x of 1 e power j omega naught t, and if I put x of minus 1, then I will get e power minus j omega naught t. So that is, these are the only two values which I am going to get. I think I am supposed to write e here, e power j omega naught t minus. Okay, so that means apart from minus infinity to plus infinity, so the value of k is present only for plus 1 and minus 1. So if I put minus 1, I'll get x of minus 1 e power minus j omega naught t. If I put k is equal to 1, I'll get x of 1 e power j omega naught t. Now if you compare this two with the given x of t here, so this e power j omega naught t, e power j omega naught t is same. In place of x of 1, what do we have? 1 by 2j. Now in place of x of 1, I have minus 1 by 2j, and the remaining is same. Okay, so that means while directly comparing this with synthesis equation, we will get the values of x of k, that means for which values of k is present. Understood. Now based on this, when comparing this with the equation, we get x of 1 is equal to 1 by 2j, and x of minus 1 is equal to minus 1 by 2j. Okay, so apart from these values, for the other values of k, there is no signal existing. So that means we can write for x of k will be 0 for values of k which are not equal to plus or minus 1. So apart from these two values, plus 1 and minus 1, x of k will be 0. Okay, so this is the conclusion. So based on this, so comparing this with the synthesis equation, this is for understanding purpose. I have elaborated this. We'll go with the same approach for the remaining problems as well. Most of them, we'll just try to write the synthesis equation and we'll compare this. Okay, we get x of 1 and x of minus 1. Now these are the two values of x of k which are present, and remaining values for k, x of k will be 0. Now if you want to plot the magnitude spectrum, so first thing is we have to find this magnitude of x of k. Now observe this, we have x of 1 is equal to 1 by 2j. Now this j, this can't be in the denominator, because we can take the magnitude if we have something in the form of a plus ib, or x plus iy or jy. That is, if it is in this form, so you can take this as square root of a square plus b square to find the magnitude of these two. Now this j is in denominator, so that means this can't be happening. We have to bring this to the numerator. So for that we have to deal with the denominator first. So how to deal with this means, we can go by rationalizing the denominator. That means if you have something like this, x1 divided by x plus jy. Now, so what we do, we take this x plus jy, so we equivalent way. So we just multiply with the complex conjugate of this, both numerator and denominator. So that is x minus jy, x minus jy. So whatever I have in the denominator. So this is what you call it as rationalizing the denominator. Okay, so I am explaining this in the first problem, and later case you have to deal these kind of things frequently. So this is the first problem, so I am explaining this rationalizing the denominator method, and remaining problems I won't be elaborating that much to save much the time here. Okay, now in the given problem, x of 1 is 1 by 2j. Now this we can write it as 2j, because the real part is 0. So if you multiply by this, you'll get minus 2j and minus 2j. Or you can keep this 1 by 2 separately, and you can just take the j part multiplied by 1. So that gives you j into minus j, and in the numerator it will be minus j only. So if you simplify this, you will get minus 4j square. Numerator is minus 2j. Minus minus will get cancelled. 2 to 2 za. So you will remain with here we have j here, and the denominator is j square here. Now the value of j is square root of minus 1. So if you take j square, then its value will be minus 1. Okay. So if j is equal to root of minus 1, so j square will become just minus 1 here. Okay. So that gives us with, so we have 1 by 2 j here, and j square value is minus, I am writing minus here, and this j will remain in the numerator, or you can write it as minus j by 2 or minus 1 by 2 into j. So this is the value of x of 1. Now if you take the magnitude of this, I think I have written magnitude here. No, now I will take the magnitude of this. Now if you take magnitude of x of 1, so what we get? Square root of so 1 minus 2j is equal to square root of 0 plus 1 by 2 minus 1 by 2 square. Okay. So since it is mod, I will take the plus only, and you will get 1 by 2 at x of 1. Now in the same way, x of minus 1 is equal to minus 1 by 2j. So rationalize this, you will get minus of 2j into minus 2j minus 2j. So I will get minus 2j divided by minus 4j square. Here will get cancelled 2, 2. So I will get minus of minus 1 by j by 2. So minus into minus will give you plus here. So you'll get 1 by 2j. So this is x of minus 1. So therefore, if you take the magnitude of this, so again it is square root of 0 square plus 1 by 2 square. Again you will get 1 by 2. Now if you plot this magnitude, okay, where here the index is k, and we are trying to plot magnitude of spectrum x of k, 0. I'll take some values here, 1, 2, 3, 4, and I'll take negative values. This is the origin. Now these are two present at x of minus 1 and x of plus 1. So what are the values here? At x of 1 we have 1 by 2, and x of minus 1 we have 1 by 2 as well. So that's the value we have here. We have a signal with amplitude 1 by 2 at x of 1, and we have another signal spectrum at minus 1 with amplitude 1 by 2. So this is magnitude spectrum. Now if you go for phase spectrum, so it is denoted by phase of x of k. That will be equal to tan inverse of b by a. Now you always now consider these values while plotting the phase. That means after performing the rationalization of denominator, we have x of 1 is equal to minus 1 by 2 into j. So that allows us tan inverse of the real part is 0, and the imaginary part b is minus 1 by 2. So minus 1 by 2 divided by 0. That gives us tan inverse of I think minus infinity. That will be equal to minus tan inverse of minus infinity is minus pi by 2, and for x of minus 1 we have 1 by 2 j, that is tan inverse of 1 by 2 divided by 0 here. So that is tan inverse of plus infinity, that is plus pi by 2. So at x of minus 1 we have pi by 2 and x of plus 1 we have minus pi by 2. So let's plot this here. So this is phase x of k. So 1, 2, 3, 4 and minus 1, minus 2, minus 3, minus 4. So at plus 1 we have a signal with the value minus pi by 2, and here we have a signal with value plus pi by 2 as per the calculation. So this is how we are going to find the Fourier series of the expression and plot magnitude and phase spectrum. Okay. Now I have one more problem, another kind, a simple one. So given x of n is equal to, sorry, x of t, continuous term, x of t is equal to sine 2 pi t plus cos 3 pi t here. So the problem is find the Fourier series representation and plot its magnitude and phase spectrum. So this is the problem. So here, so we are dealing with periodic signals only. Now, if you observe this, given signal is the addition of two different type of signal with a different frequency, that is angular frequencies are changed here, not the same. In the previous one we have one signal with angular frequency omega naught, here it is different here. Now how to deal with this? So given x of t is equal to sine 2 pi t plus cos 3 pi t here. Okay. Now for this, if you compare this with sine omega naught t plus pi, so this is the representation of sinusoidal signal, and this with cos omega naught t plus pi. I'm just writing here. If you compare this and this, both are sinusoidal signal. In place of omega naught we have 2 pi here, and here we have 3 pi. Okay. Since we have two signals, just to differentiate them, I will write omega naught is equal to 2 pi, and I'll write omega naught 1 here. Omega naught 2 is equal to 3 pi. Okay. Now we should have a common frequency, angular frequency for both of them. Now for this kind of signal, that means combining these two, we are getting x of t. Now what is x of t? X of t will have one frequency, angular frequency, that is omega naught. Now this can be found if you have two different values of omega. So we can find like this. We can take the greatest common divisor of these two. Okay, 2 pi and 3 pi. And for this 2 pi and 3 pi, if you take, so it will be the common divisor, right? To will get pi 1 into pi, or you can say, so you can do 1 2 is 1, so that is 1 means 1 into pi. So omega naught will be equal to pi here. Okay, so that will be our frequency, angular frequency. Now expressing these two, sine 2 pi t in terms of exponential and both cos 2 pi t. We can write like 1 by 2j. I am directly writing this e power j 2 pi t minus 1 by 2j e power minus j 2 pi t. So this is the sign conversion into exponential, and this one is 1 by 2 e power j 3 pi t minus, sorry, not minus, plus 1 by 2 e power minus j 3 pi t here. Okay. So combining these two, x of t is equal to, first I will write sine version of this, 1 by 2j e power j 2 pi t minus 1 by 2j e power minus j 2 pi t. Now plus 1 by 2 e power j 3 pi t. So this is the cos version, plus 1 by 2 e power minus j 3 pi t. Okay, let's compare with the synthesis equation of Fourier series. So we have x of t is equal to summation k is equal to minus infinity to plus infinity x of k e power j k omega naught t. Now observe this summation here. So in place of x of k we have 1 by 2j minus 1 by 2j, and here 1 by 2 and 1 by 2, so that is fine. Now these values are present for which value of k? So observe this here, we have omega naught, so that is omega naught value is pi, so we have pi here, here, here and here, and j and t are common in all of them. In place of k, if you observe this, we have plus 2 here and we have minus 2 here, plus 3 here, minus 3 here. So that means we have 4 values of x of k. So that those are x of 2 is equal to, so the first one is x of 2, that is 1 by 2j, comma, second one is x of minus 2 here, so this one is having minus 1 by 2j, and the next one is x of 3, take this one, x of 3 plus 3 is there, in place of x of k we have 1 by 2, and finally x of minus 3 is equal to this one, so again it is plus 1 by 2 only. So these are the 4 values. Now here observe, we have, so these are the values for x of k, the Fourier series representation of the signal. Now before going for magnitude of a spectra, observe here we have 1 by 2j and minus 1 by 2j, so this j should be taken to the numerator by rationalizing the denominator method. So in the previous problem, since I explained that, I am just writing the values here. For x of 2 we can write, so this becomes minus 1 by 2 into j, and for x of minus 2 I can write plus 1 by 2 into j, and x of 3 we have no imaginary term, so it is just 1 by 2 here, and x of minus 3 is again 1 by 2. So these are the values. Now let's go for magnitude spectrum for this signal. So if we take the magnitude spectrum, so first one for x of 2 we have minus 1 by 2 into j, so that will be square root of 0 plus 1 by 2 square, again it is 1 by 2, and for x of minus 2 it is 1 by 2 into j, again root of 0 plus 1 by 2 square, So we will get 1 by 2 here. Since it is magnitude, we have to consider only the positive values. And for x of 3, it is 1 by 2. So you will get 1 by 2 square plus 0. Again, it is 1 by 2. And for x of minus 3, it is 1 by 2. So that is 1 by 2 square plus 0. Again, it is 1 by 2. Now I will plot the signal here itself. So the values for this, I'll take 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4. So at x of 2, we have 1 by 2 here. X of 3, we have 1 by 2 here. And x of minus 2, again it is 1 by 2. And x of minus 3, again it is 1 by 2. So we have completed the magnitude spectrum. Now going for phase spectrum. So first one is phase x of 2, that is tan inverse of minus 1 by 2 by 0, that is tan inverse of minus infinity minus pi by 2. So x of minus 2, we have I think plus 1 by 2j, that means tan inverse of 1 by 2 by 0, that is tan inverse of infinity. Again you will get plus pi by 2 here. Next, x of 3 is 1 by 2, the real value tan inverse of 0 divided by 1 by 2, that is tan inverse of 0 value will be 0 only, and x of minus 3 is 1 by 2, it is tan inverse of 0 divided by 1 by 2. So again it is tan inverse of 0 and it is 0. So we have values only present for x of plus 2 and minus 2, and for x of 3 and x of minus 3 it is 0. Did I mention the, yes, okay. So this is the phase spectrum. So 1, 2, 3 and 4, minus 1, minus 2, minus 3, minus 4. At x of 2, we have the value minus pi by 2, and at x of minus 2, we have plus pi by 2, and here we have 0, and here we have 0. So this is the phase spectrum for the signal. Okay. So moving on to the next step. Here we have a different kind of signal. So the signal is represented graphically. So let me write it down. Okay. So for this problem, I want you to try the magnitude and phase spectra. Anyhow, let's take the problem here first. Okay. So this is 0, 1, 2, 3, and the signal will continue 4 and etc. And this is minus 1, minus 2, minus 3, and this is just, it's a periodic signal. So this part is given as x of t with an amplitude 1, and here the signal is represented, it's a decaying exponential e power minus t. Now this is the given signal. Now for this, again we have to find the Fourier series representation, and we have to plot magnitude and phase spectrum. So sometimes they'll just ask draw its spectrum. Okay, so that means we have to plot both of them. So this is the given signal, and the entire signal, it's a periodic signal, as you can observe. Now since it's a periodic signal, the signal is from 0 to 1. Either after 1 division or 1 time duration, the signal is repeating the same. So that gives us the fundamental period t is equal to 1 here. So therefore omega naught is equal to 2 pi by t. So that is 2 pi by 1, that is 2 pi. So omega naught is equal to 2 pi and t is equal to 1. Now for this problem, I will take the analysis equation, that is x of k is equal to 1 by t integral of d x of t e power minus j k omega naught t dt. Now this signal is periodic, so we have to consider one duration, and here you can take any one particular duration. You can take from 0 to 1, 1 to 2, 2 to 3, 3 to 4, or you can take from minus 1 to 0 or minus 2 to minus 1, any one particular duration as you wish. Okay, so I will start with 0 to 1 here. You can try with some other duration of the signal. Anyhow, the result will be the same, no change in that. So t is equal to 1 here. So 1 by 1, I will take 0 to 1. In that particular duration, 0 to 1, what is the signal here? The signal is e power minus t here given. X of t is e power minus t between 0 to 1 or 1 to 2, whatever it is. Let's substitute that e to the power of minus t into e power minus j k, and omega naught value is 2 pi t dt. Okay, now we have common base here. So let's combine this. I am not continuing this with further. So 0 to 1 e to the power of the value is minus t, and here both minus I am taking common. That allows me 1 plus j 2 pi k into t dt. Okay. So now if you integrate this, it will be minus e power minus 1 plus j 2 pi kt divided by j 2 pi k with limit 0 and 1. Okay, so this is my x of k. You can go with the synthesis equation also to find it. Anyhow, I am showing you both of them. In the previous two problems, I took the synthesis equation. Here, I am taking the analysis equation. So both you can take and you can apply this. But for these kind of signals, it will be better. You can go with analysis equation. If you integrate this, and I just apply the limit here. So we have e to the power of j 1 plus j 2 pi k t divided by j 2 pi k is there. So that we are supposed to simplify by applying the lower and upper limit. And let me do that step here. Minus e power of 1 plus j pi k minus e power of 0. So this entire term is divided by j 2 pi k. So if I'm doing like this, let me take this out here because I can write the minus separately. So let me mix it as 1 here, and this one is e to the power of minus 1 and e to the power of j 2 pi k can split plus 1 divided by j into 2 pi k. This term g cos 2 pi. So this exponent, if you convert this into trigonometric function, that will be cos 2 pi plus j sin 2 pi, that will be 1. Okay, so I'll write the final answer here. 1 minus e to the power of minus 1 divided by j 2 pi k. So this is x of k here. Or you can further simplify this with 1 minus the value of e to the power of minus 1. I think you are going to get this as some 0.3 or 0.6, I guess. 0.3678 divided by, that is j 2 pi k here. Now if you continue this, I think it is 1 plus, right? I forgot this 1 plus here in the denominator. So we have 1 plus in the denominator, which I forgot to mention. So 1 plus j 2 pi k. Let me keep it as simple. So 0.6322 divided by 1 plus j 2 pi k. Okay. So now this is x of k here with the simplest form. Now for this you have to draw the magnitude and phase of the signal. Let's try with this, find the values for since it's a periodic signal. In the previous case we had only 3 or 4 values. For here we have to draw the signal for periodic signal, means for every one duration. So let's take some 2 to 3 divisions in the positive axis, another 2 to 3 divisions in the negative axis, just to know how the signal will look like. Like you can go with for magnitude spectrum, you can go with from -3 to +3 for both the magnitude and phase spectra. That will allow 7 samples, 7 values to deal with. So find out x of 0, x of 1, x of 2, x of 3, and x of -1, x of -2, and x of -3, the values of that, and get the magnitude values and plot the spectrum here. Anyhow, I will give the values for you to verify. For this x of 0, you will get 0.63, x of 1 you will get 0.1, and x of 2 you get 0.05, and x of 3 you get 0.03. It is starting decaying, and x of -1, again you will get the same value 0.1, x of -2 you will get same 0.05, and x of -3 you get 0.03 here. So same values. Now plot this graphically, and for phase spectrum, so for x of 0 you will get 0 here, for x of 1 you get -1.41, and for x of 2 you should get -1.49, and for x of 3, you get minus 1.52. So these values I'm giving you for your verification process. Try this uh, as we did in the last two problems and try to get the answer. Verify whether you are getting the same or nearby values, also fine. Okay. So this is how we deal with the problems on Fourier series by different approaches. And magnitude and phase spectra we will get commonly asked to plot in most of the cases. So try to be familiar with the method. And if you have any queries regarding this method of solving the problem, do reply or comment to the video. Thank you for your time.